Hey guys, welcome to video number 24. Today's topic is first order RC filters. Before we actually look at the filter circuits, let's just review some basic filter concepts. A filter is a frequency selective circuit that's designed to pass a certain range of frequencies while rejecting or attenuating all others. We quantify the response of a filter through the ratio of its output to its input as a function of frequency. Usually we're interested in voltages, so that's going to be V out over V in. For amplifiers, V out over V in is voltage gain, and that's usually represented as A sub V, or sometimes just G. When we're dealing with filters in particular, V out over V in is often represented with the letter H. We're not going to worry about the distinction between these for today. We're just going to go with V out over V in. Now there are 5 fundamental filter response types: low pass, high pass, band pass, band stop, or sometimes called a notch filter, and all pass. Today we're just going to be concentrating on low pass and high pass, so don't worry about these 3. We'll talk about them some other time. All right, the low pass response over here has 2 frequency ranges of interest: the pass band, which is all the frequencies the filter lets through, and the stop band, which is all the frequencies the filter blocks. The point that divides these 2 regions is F sub C, the critical frequency of the filter. Now sometimes we'll call that the corner frequency too, because we do have a corner here, and other times we might call that the half power frequency. All right, the inverse of the low pass filter is the high pass filter, and we can see the difference is the pass band and stop band have exchanged places, but they're still separated by the critical frequency. All right, now something I want to mention before we go on is the response shapes that I have shown here are what are called brick wall responses. Okay, an ideal filter would have a brick wall response. In real life, no filter can have this perfect response, so we approximate it by using different orders of filter. The least accurate approximation to a brick wall response is going to be a first order response. If we want to get better and better approximations, we go to higher and higher order filters. Now, what determines the order of a filter? Well, the number of energy storage components in the circuit determines the order. A first order filter has 1 energy storing component, so that's either one capacitor or 1 inductor. A second order filter would have 2 capacitors or 2 inductors, or maybe an inductor and a capacitor. And we can just keep going, adding more capacitors and or inductors to get higher order filters. All right, let's look at our first order RC low pass section. All right, we're using a capacitor and we're driving the circuit with a sinusoidal voltage, so we can use phasor algebra to figure out what's going on here. The output voltage is given by the voltage divider equation, which we have shown up here. At very low frequencies, the cap acts like an open circuit, and we get this equivalent where the output voltage equals the input voltage. So at 0 Hertz, V out over V in equals 1. That's our maximum response. As frequency goes up, the capacitor shorts more and more of the signal to ground, and it begins looking more and more like a short circuit, so the output voltage approaches 0. In the limit, the capacitor is a short to ground. Okay, now let's talk more about the critical frequency. All right, the critical frequency of this filter is defined as the frequency at which the magnitude of X sub C equals R. So if we equate these 2 quantities and solve for F, the critical frequency equation is 1 over 2 pi RC. Now this is a really super important equation. We're going to see it a lot in future videos. So this is one that's actually worth memorizing. I'm not one that's big on rote memorization, but this equation is worth memorizing. All right, now if we look at the response curve, we see at 0 Hertz the response is 1 and it begins dropping off, and at the critical frequency the response is down to 0.707 times the max value. Now why is that? Well, let's come over and look at this circuit, and for the sake of convenience, I'm going to set R equal to 1 ohm. And if we're operating at the critical frequency, X sub C is also equal to 1 ohm. And if we plug those values into the response equation in rectangular form, we've got negative J over 1 minus J. All right, we want to find the magnitude of this expression. All right, so the magnitude of the numerator is simply 1, and the magnitude of the denominator is going to be the square root of 1 squared plus 1 squared, which gives us 1 over the square root of 2. All right, so at the critical frequency, the response is equal to 1 over square root of 2, which is approximately equal to 0.707. So that's where this value comes from. All right, let's go down and look at this circuit on a clean sheet. And I'm going to derive an equation that tells me the frequency response of this circuit in terms of R and X sub C. All right, so I'm going to repeat this expression up here, V out over V in. And in polar form, this would be X sub C at negative 90 degrees divided by R at 0 degrees plus X sub C at negative 90 degrees. Okay? We've seen that many times before. And the rectangular form is going to be negative J X sub C over R minus J X sub C. Now what I'm going to do is substitute this denominator over in this form, which gives me X sub C at negative 90 degrees over R minus J X sub C. All right, I'm going to find the magnitude and phase angle of the denominator. So I have X sub C over at an angle of negative 90 divided by the square root of R squared plus X sub C squared at a phase angle of the arctangent of negative X sub C over R. Okay, now I'm going to separate out the magnitude, which is just X sub C over the square root of R squared plus X sub C squared. And remember, when we do a division, the phase angles, we subtract the denominator from the numerator. So the overall phase angle here is going to be negative 90 degrees minus the arctangent of negative X sub C over R. All right, now that's pretty messy, so I'm going to clean up this angle a bit. And what we end up with then is X sub C over the square root of R squared plus X sub C squared at a phase angle of negative arctangent R over X sub C. All right, now that's not exactly the nicest equation in the world, but it is an equation that tells us the response of this circuit. Now I could back substitute the expression for X sub C into this thing and massage it algebraically to get a form that gives me the response in terms of the critical frequency and the input frequency. But rather than drag you guys through my messy writing and the algebra, I'm just going to present that form over here. All right, so V out over V in can also be determined through 1 over the square root of 1 plus the quantity F in over FC squared at a phase angle of negative arctangent F in over FC. All right, so we have two different equations we can use. This one or this one. All right, now this is horribly messy and hard to read, so because I love you guys so much, I did a nice typeset version of it, and I'm going to drag that over here once I clear the decks. Okay, and there we go. Here's a nicer version for you guys. You can do a screen grab of this. It'll give you all the pertinent information. And there you go. All right, so this is the first equation I derived, gives us the response in terms of R and X sub C, and we can also convert it into a response in terms of Fn, the input frequency, and the critical frequency. All right, let's apply this equation now to an actual circuit. All right, so on the next page here, I've got a first order RC section driven by a 10-volt peak sine wave with an indeterminate frequency here, but what we're going to do is just figure it out for these three different frequencies. All right, so first let's find our critical frequency. Okay, FC, let's pull up our calculator, and that's going to be 2 times pi times 1500 times 0.1 times 10 to the negative 6th power, and we take the reciprocal. Our critical frequency is about 1061 hertz. Okay, now we're going to apply this equation to determine the response at each of these frequencies. Okay, so let's start at 500 hertz. Inside the parentheses here, we've got 500 divided by the critical frequency, which is 1061. We're going to square that, add 1, and take the square root, then the reciprocal, and we get a response of about 0.9. So the magnitude of the output is 0.9 times the input, so that gives us 9 sine 2 pi 500 t, and we're going to have a lagging phase angle. Let's figure out what that is. All right, so we've got the arctangent of Fn, which is 500 divided by FC 1061. We'll take the arctangent, which gives us 25.2, so it's negative. Our phase angle is negative 25.2 degrees volts. So there's our output with a frequency of 500 hertz assigned to this input, 9 sine 2 pi 500 t minus 25.2 degrees volts. All right, let's do it at frequency of 1 kilohertz. So starting with the magnitude, Fn is 1000, and that's divided by FC, which is 1061. We're going to square that, plus 1, take the square root, and now the reciprocal, and we get a response of about 0.73. All right, so our output voltage is 0.73 times 10, or 7.3 volts, sine 2 pi 1000 t. And now let's determine our phase angle, which is the arctangent of 1000 divided by 1061, and that is about 43.3, and it's negative, so this is minus 43.3 degrees volts. All right, so our output at 1 kilohertz is 7.3 volts peak, lagging by 43.3 degrees. And lastly, we'll find it at 10 kilohertz. All right, so finding the magnitude, 10,000 divided by 1061. All right, we're going to square that, add 1, take the square root, and then the reciprocal, and our response is now 0.11. So that would be 0.11 times 10 is 1.1 sine 2 pi 10,000 t minus a phase angle of, all right, 10,000, whoops, not 100,000, 10,000 divided by 1061, arctangent about 84 degrees. So we're going to be lagging by about 84 degrees here. All right, so with 10 kilohertz assigned to this frequency, our output is 1.1 volts peak, lagging by 84 degrees. All right, so that's much easier generally than going through phasor algebra for each different frequency, and that's the advantage of having an equation like this. All right, now lastly, let's switch gears and talk about the high-pass filter. To convert this to a high-pass, all we do is interchange the resistor and capacitor. All right, it doesn't change the critical frequency. It's still 1 over 2 pi RC, but our response equations change a little bit. Okay, of course we've got R in the numerator of this one because that's where we're taking our output voltage, and we also flip over the fraction in the arctangent. Likewise, for the response in terms of F in and F sub C, we just flip over the frequency fraction and we get the response equation. And here's what it looks like as a function of frequency for the magnitude of the response. Okay, so we're going to be using RC sections like this quite a bit in future applications. And now we've got, I think, a pretty good handle on the basics of how they work, and we'll discuss more about them as necessary in the future. So that's it for today's video. I will see you guys the next time.